The first derivative is a very powerful tool in helping us to understand how a function behaves, where a function is increasing, where it's decreasing. We can use the first derivative test to identify maxes and mins. But what does the second derivative contribute? That's what I want to explore with this video, and I want to do so with two functions. F of x equals x squared on the interval 0 to infinity. Now, notice this function on that interval is always increasing. From left to right, this function's always going up. Now, the other function I want to use for this video is the square root of x, g of x. I'll call this g of x. Now, notice this function is also always increasing on this interval from 0 to infinity. So this is something that these two functions have in common. They're both always increasing. In other words, the first derivative is positive from 0 to infinity for both of these functions. Except, at 0 for the square root function, the first derivative doesn't exist. But on the open interval, 0 to infinity, these are both first derivatives positive. Now, let's start off by just looking at f of x equals x squared. And what I want to do is I want to look at what happens to y per unit change of x. In other words, I want to look at how y changes as I plug in x equals 1, x equals 2, x equals 3. I want to look at how the function changes from f of 1 to f of 2 to f of 3 and so forth. This is what I mean. Let's suppose I want to go right here at x equals 1. Okay? Now this line here represents, it's a picture representation of the amount of change that takes place in the function as x changes 1 unit. So I'm going from 0 to 1, and look at what y does. Y goes from here to here. Now let's look and see what happens as we go from x equals 1 to x equals 2. How much change takes place in the y? Well, we start here, right? Now let's see how much change takes place. Okay, this much, right? That's a picture of it. Now what about from 2 to 3? We start here, right? 2. And we come over here to 3, how much change takes place in the y? That much, right? See, look at that. Now let me turn off the function and just look at these. These lines, notice they get longer and longer. And if we said, well, how much change takes place from 3 to 4, you would see even a longer line. So let me turn back on the graph and let's just look at something here. The particular shape of this graph, notice the fact that we keep changing 1 unit on the x, but the y gets larger and larger, tells us that the first derivative is increasing. The rate of change is getting more and more. In other words, this function is increasing, right? F of x is increasing, but what I'm saying is f prime is also increasing. F prime is also increasing on this interval. You can see that. See? Because I've just got unit measurements here on the x, you can see what the average rate of change is, or what the rate of what the change is. So you can deduce from that, well, the rate of change is increasing, right? Because I'm going from here up to here, from here to here, and it just gets greater and greater. As x changes just units, the y gets a greater change. Okay, now let's leave that and look at, let me turn these off, and let's just look at the square root function. Okay, here's the square root function. And I want to look at how much the function changes at x equals 1. So I'll just go back and turn this one on. Here we go. So from g of 0 to g of 1, that's how much change takes place in the y as x changes 1 unit. Now let's look at as x equals 2. Okay, there it is. You can barely see it. Let me blow it up a little bit here. Okay, see? Here's the change when x is 1. Here's the change when x is 2. See, we went from g of 1 to g of 2. Look at that. Now let's try g of 3. There that is. Now notice it's a little shorter. See how these are getting smaller? They're getting smaller. Okay? Let's try 4. See, even smaller. Now let me turn off the g function here. Okay, there, I turned it off. Now look, these lines are getting smaller and smaller. That tells you that the rate of change is decreasing. In other words, what's happening is the first derivative is not increasing like it was with x squared. It's decreasing. Now, look at this. This function is said to be concave down. And when you have a concave down function, what you have is a decreasing first derivative. Okay? So the first derivative is, it's positive, yeah, because this function is increasing, but it's decreasing. Now contrast that. Let me turn off all these little lines here. Now contrast that with x squared. This function is concave up. It's opening up. When you have a function opening up like this, concave up, it means that the first derivative is increasing. So this function is increasing, right? See it, it's increasing. And it's increasing at a faster and faster rate. So the first derivative is increasing, therefore the second derivative must be positive, okay? First derivative increasing, second derivative is positive. Now, let's look at the second one down here. This one, first derivative is positive, yeah, because it's increasing. However, it's decreasing. Yeah, the first derivative is positive, but it's decreasing. That means the second derivative is negative. So let's look at a bit of an example here. I've got this function right here, okay? Now, notice that this function is increasing all the way to this number, x equals -5. See that? The function is increasing. So -5 and -2, those are both critical numbers. And we would say this function is increasing from -infinity to -5, and then from -2 to infinity. So increasing here and increasing over here. Now it's decreasing here, okay? All here. Now, here's what I want to point out. The first derivative, if we're talking about the first derivative and we want to know where is the first derivative positive, well, it's positive from -infinity to -5 right here, okay? And also from -2 to infinity, see, because that's where the function is increasing. Now, if we're asked where is the first derivative negative, from -5 to -2. But what about the second derivative? The second derivative. If we want to know where is the second derivative positive, well, the second derivative is positive whenever we look at the graph and see concave up. Okay, so look at this, opening up right here. This is concave up. This is where the second derivative would be positive, right there, for these values for x. Where is the second derivative negative? Well, over here. Here's where it's negative, right here. Now, at some point, we go from concave down, opening down, to concave up. Maybe, just eyeballing it, maybe along here. This right here, where it transitions from opening down like this, concave down, to concave up, that point where that transition happens, that value for x, that's inflection. So at somewhere along here, it looks like there is an inflection point. The inflection point is that point where you go from concave up to down or concave down to up. That's the inflection point. Now, So how would that look in this graph? You have concave down right here. See that? The second derivative is negative there. Here you have concave up. The second derivative is positive. At somewhere about here, you go from second derivative negative to second derivative positive. That would be the inflection point where that happens, where the second derivative changes signs from negative to positive or positive to negative. Okay. Now I want to point out something to you here, and this is going to be the second derivative test. You notice that we have -5, that's a critical number, and -2, that's also a critical number. In other words, those are numbers that you get when you set the first derivative equal to 0 and solve. You get x equals -5, x equals -2. Those are critical numbers. And the first derivative test said if your graph goes from increasing to decreasing at that critical number, then you know you have a maximum. If it goes from decreasing to increasing at that critical point, putting in the -2 into the f. In other words, this is the critical point right here, and -2 is the critical number. So this right here is the critical point. But notice, as x goes from -5 to -2, the first derivative is negative. Then at -2, it switches to positive because the graph goes from decreasing to increasing. Now, the second derivative. So now let's talk about the second derivative test. Notice where you have a maximum, you have concave down. See that? Here you have concave down. Where you have a minimum, you have concave up. So here's the deal with the second derivative. You take the critical numbers that you got from the first derivative by setting it equal to 0. You plug it into the second derivative. And if the second derivative gives you a negative number there, then that means that critical number corresponds to a maximum because your graph is concave down at maximums, right? Now, if you plug that critical number in, like in this case a -2, into the second derivative, and the second derivative is positive, that indicates you have a minimum. See? Because you have concave up there. So let's look at an example. How we would use calculus, the first and the second derivative, to analyze the graph of a function. So here, let's use this one. We've got 1/3 x cubed plus 5/2 x squared minus 6x plus 1. Now, I want to answer this question first, these questions first. Where is this graph increasing? Where is it decreasing? And where are the maximums? Where are the minimums? I do that with the first derivative. I answer those questions with the first derivative. So, and to do that, I need to find the critical numbers. So here I go. I need to take the derivative. This is our starting point. So we get x squared plus 5x minus 6. I just differentiated this. Now, I set that equal to 0 and solve for x. Okay, so I'm going to go ahead and factor it. There we go. There's the factorization. And we get x equals 1 or x equals -6. These are critical numbers. Now, what I do with those critical numbers is I like to use those to divide up the number line. Everything less than everything less than -6, everything between -6 and 1, and then everything, greater than 1. So this is the way I've divided up the number line. And I pick test numbers in each region. So here's -7. This one right here, I'll pick 0. 0 is always a good one. Not always, but unless it's going to make the denominator 0 or something. But anyway, I don't want to digress. Then we pick a number over here. So pick 2. There we go. Okay, now here's what I want to do. I want to test these, I want to put these test numbers into the derivative, not the original function, but the derivative, because I want to see if the derivative is positive or negative at those test values. So here I go. I've got x, and then I've got x minus 1, x plus 6, and let's see here. I've got negative 7, 0, and 2. Okay? So I put in a negative, and I get a negative right here. Put in a negative, I get another negative. See, I don't really care about the value, the numerical value. I just care about, is it positive or negative? And here I've got negative times a negative, that's a positive. So here I got positive. That means this function is increasing here. So let me just put that for emphasis. It's increasing. The function, this f of x, this is increasing. Now, let's look at what happens when I put a 0 in here. Well, I get a negative times a positive, give me a negative, so this is negative. Negative right there, and that's decreasing. Now, what about a 2? Well, I get a positive times a positive, gives me a positive. That means positive here, and I'm increasing. Okay, now, here's what we can determine from this. We know where the graph is increasing. It's increasing from negative infinity to negative 6. Unioned with 1 to infinity. See? Right there. You can see that. Now it's decreasing from negative 6 to 1. Like that. Okay, so that's where the function is decreasing. Now, I'm going to apply the first derivative test now. The first derivative test tells us that a max occurs right here. Okay, a max occurs at x equals negative 6. And that max value is f of negative 6. Now, a min occurs at x equals 1, and that would be f of 1. This is the max value, this is the min value, and this is where they occur. So we wouldn't say the max is x equals negative 6. No. That's where the max occurs. See, the min is f of 1. It occurs at x equals 1. Okay. So this was the first derivative test right here. Now, let's look at the second derivative. So now we're going to answer the question of concavity. Okay, on concavity. So here we go. I'm going to go back and get my function here and differentiate it again. So here we go. F double prime is 2x plus 5. Now I do the same thing I did earlier, except now I'm not getting critical numbers. I'm getting possible points of inflection. So here I go. I got 2x plus 5 equals 0. That gives me x equals negative 5 halves. X equals negative 5 halves. Now, I repeat this same thing, deja vu here. We're just going through the same process again. I'm going to pick numbers less than negative 2.5, maybe negative 3, and then numbers bigger than negative 5 halves, which I'll just pick 0. And this time, I'm going to plug those numbers into the second derivative because I want to see if the second derivative is negative or positive. Okay, if I plug in a negative 3, I get a negative, right? Negative 6 plus 1. If I plug in a 0, I get a positive. So here's what we got. We got negative here. This is concave down. We got a positive here. This is concave up. This is definitely an inflection. This is where an inflection occurs. So let's see if we can put this all together. When we talk about the graph being concave down, And if we're asked, where is the graph concave down? Well, another way to ask that is, where is the second derivative negative? On which open interval is the second derivative negative? Well, we've identified that right here. Negative infinity to negative 5/2. Okay, now we want to say, okay, well, where is the graph concave up? In other words, on which open interval is the second derivative greater than 0? Well, here it is right here. See? So it's going to be negative 5/2 to infinity. There it goes. Concave down, concave up. Now, here's the second derivative test. Let's go ahead and apply the second derivative test. Now, really, we've already determined up here with the first derivative test that a max occurs at x equals -6 and a min occurs at 1. So we're just kind of using the second derivative, we're trying to practice using the second derivative. So we're going to verify our results up here. So I'm going to take f double prime of -6. Now remember, a max occurs there. So the second derivative should be negative there. Okay, because that gives us a max. So here we go. 2 times -6 plus 5. Yeah, that's definitely less than 0. So yes, the second derivative test confirms, yeah, there's a max there. Now what about f double prime of, what was that other one? It was 1, x equals 1. Well, if we put that in, we get 2 times 1 plus 5, and yeah, that's definitely bigger than 0, so a min occurs there. So that's the second derivative test. Now, if we would have plugged in one of the critical numbers and got the second derivative equals 0, then we would just say, okay, that second derivative test is not going to help us here. It's inconclusive. We don't know. But if you get a second derivative less than 0, indicates a max, greater than 0 indicates a min.